and we're going to look at double integrals in section 13.2. We're going to look at functions f of x, y. We're going to let these be nice functions. So these are going to be continuous, differentiable with respect to both x and y, etc. Is kind of the intent here. And if you remember in 3 space, you know, x comes out of the board at us, and y is to the right, z is up. And really what I want to do is I want to look at that table surface. And so let me just kind of focus on that a little bit, and let's just draw it back in the old x, y, where x is to the right and y is up. And if I want to look at a region here, R, we're going to call it region R. Notice that's not a bold R, it's just an R for a region. That's a rectangular region, and we go from 2 points. Now, back when we had a definite integral and we were looking at area under the curve, if you remember that, what did we do? We went from A to B. So in this case, what the book does is they say, hey, let's go from A1 to B1 for the x's. And then, but we have 2 variables here, so we're also going to go from A2 to B2 up here. And so what they do is they say, hey, let's look at the lower left and the upper right, call this A and call this B. Well, point A is going to be given by over A1 up A2, and point B, the upper right part of the diagonal, is over B1 up B2. So they do that, and then they're going to look at the length of the diagonal there as a measure of this rectangle. Of course, we could look at the area too, which we will. So here's kind of just give you a heads up. When we actually get into evaluating integrals, they do this because, you know, before we went from the definite integral from A to B, right? So we were doing that definite integral from A to B of f of x with respect to x, and if f was entirely on or above the x-axis, then this was actually the area. So we're going to do similar things, but what I'm going to do is I'm going to say, hey, instead of A1, I might call that X1. Instead of B1, I might call that X2 because I'm following the x-axis here. And I may do something similar over here. Instead of going from A2 to B2, I may call that, hey, Y1 to Y2, where, you know, X1 is less than X2 and Y1 is less than Y2. So let me clear that off. So I think that's what I want to do here. And let's just kind of look at a big region in here. So let's look at a rectangular region R, and let's just say, you know, it's when x and y are both positive. But anyway, here's my region R, and I'm going to go from x1 to x2, and what I want to do is I want to split these up. I want to use different widths here, split this up. For some reason, not writing the whole time. And normally when we, you know, if we want them all to be the same, we call that delta x. And if we had n such partitions here, then what was delta x? It was b minus a all over n. Well, in this case, it'd be x2 minus x1 all over n if they're the same width. But the reality is, Riemann sums, we're going to have different widths here. So I'm going to call this delta sub I x. And if I want the widest subinterval, right, on that. And then I'm going to do the same thing going from y1 to y2. Here I'm going to split these up, and I'm going to let some of these be bigger than others. Okay, and we have these as well. Once again, we're going to have delta sub I y, right? And then we're going to let, so we're going to look at this rectangle. Let's take the biggest rectangle. Well, what do they mean by the biggest rectangle? We could look at the area, right, which we will, but we could look at the area of this, and what is that? The ith area there, we're going to call it delta sub I a, is the base of that, which is delta sub I x times the height, which is delta sub I y, right? Times delta sub I y. All right, so that's going to be the area there, okay? And then what we're going to do is we're going to just pick a particular point inside of there. Now we're not going to use x's and y's for that point in here. We're going to call that point just a random point u sub I, x sub I. So just, or not x, I don't want to use x, u sub I, v sub I. So that's just some random dot in there. And remember, f is a function of x and y, but what we can do is we could look at f of, instead of xy, we can say u sub I, v sub I is going to be the function evaluated at this point in this little tiny rectangular part of the region. And so we can evaluate a particular point there. And then what we can do then is look at the product of f evaluated at that point times delta sub I of a. And if I do that, and then I could add all those up. So really what I can do is I could look at the sum, I equals 1 to n. If I've got n, notice there's 1, 2, 3, 4, 5, 6, etc. rectangles. On the bottom, I got 1, 2, 3, 4, 5, 6, 7 of them. 6 times 7. I've got 42 little tiny rectangles in this big rectangular region R here. But if I look at the sum of f of u sub I, v sub I, where that's just a randomly selected point inside the tiny rectangular area, times delta sub I of a, this is actually a Riemann sum, right? So it's a Riemann sum of the product of these two things, the delta sub I of a times f evaluated at the particular point that we pick. And if I want to add all those up, I can, okay? And let's just kind of look forward here a little bit. But if this is kind of the area of the base, right? So that's area of the base. Well, if that's my table surface, and if f of x is entirely on or above the table surface, then this is kind of like area of the base times the height. So really what this is going to be like a tiny change in the volume. It's going to be a tiny rectangular solid if f is above it. And then, so that's really, we're adding up a bunch of little volumes. So we're going to be able to use double integrals to calculate volumes, just like we used a single integral to calculate area under a curve. So that's kind of neat. And then what are we going to do? We're going to let n go to infinity, or let that get bigger and bigger and bigger, or in other words, let these get smaller and smaller and smaller. So how do we do that? The book says, hey, let's take the widest, or the diagonal. Let's look at the norm of the diagonal. So let the norm of the partition, we're going to take the widest diagonal distance. And anyway, and then what we're going to do is we're going to take the limit as the norm of that goes to 0. In other words, the diagonal distance for all of these rectangles, notice that this rectangle down here is a lot smaller. So this diagonal distance is a lot less than this diagonal distance. But anyway, we want the biggest one to go towards 0. Okay, so that's what we're going to do. And when we do that, that ends up giving us essentially double integral notation when that limit exists. And so we're going to talk about, remember that region R was a rectangular region. And so what we're going to do is we're going to say that the double integral over region R of f of xy, and instead of the delta sub I a, anyway, we're just going to call that dA, is going to equal the limit as the longest diagonal goes to 0 of the sum I equals 1 to n of f of u sub I, v sub I, a particular point in there, times delta sub I of a. Okay, so, and if this limit exists, that's a Riemann sum. If that limit exists, that ends up being the double integral. And then it's going to get very similar, and it's going to be integrable on the region R, is basically what we have. Now, I do want you to notice on page 1077, they left at the bottom of the big box, blue box that they have, they forgot to include this F here. So be careful. Every once in a while, they're leaving that F out. They did that in Theorem 13.2.1. in my book, they also left it out again in the middle blue box on page 1082 for that. So the first double integral didn't have an F in it. So just look for that, fix that in your book if you don't have it there. Anyway, what's nice about this is really if I've got, this is my surface here, okay, and of course X comes, let me clear my page here. I'm going to clear this out. I'm going to show you where we're going, and then we'll hopefully do a few examples here real quick. But if I've got my table surface XY, Z is really my f of x. If I've got some rectangular region down here, and then I've got f of x, like when that comes up, and I've got some surface. So this is kind of some type of cylindrical sheet here with a surface, and then really what I can do here is if this is my I'm going to go back to the colors I was using before, but if this is my delta sub I x right here on this side, and this is my delta sub I y on this side, then really what I have here on the bottom is my area, right? So this area right here is my delta sub I a. And then what I can do, if this is f of x up here, and once again, this is a curve, but the reality is I kind of have a volume, rectangular solid there, and of course it's curved on top, but if I take the area of the base times the height, where I just pick a point here, so if I look at this height as f of, once again, u sub I, v sub I, then really what I have here is a tiny change in volume. All right, so that's going to be the volume, and then I'm going to add up a bunch of those to get the total volume. So this is instead of a sub I for the ith area, this is v sub I for the ith tiny volume. And that's how we're going to utilize this stuff. So let's look at a couple examples. Let me clear this off and go back. It's letting me write nicely now, which is good. And let's just, I'm just going to look at, we'll look at example 1 because you've got to do one like this. Number 1 is similar. It says find the approximate value of the double integral over region R, integral over region R of 3y minus 2x squared dA. Well, so anyway, so we're going to end up finding the exact area of this soon, but I just want to show this, and this they kind of specify where we want to. They're going to say -1 is less than or equal to x is less than or equal to 2, and y is going to be bounded by 1 and 3. Okay. And so really what they do is they show the x and the y basically what we did is we divided this up into 6 tiny rectangles, okay? And then picked a midpoint for each rectangle. That's what we plug into F. And then when I was just had one of them here solid, the area of each rectangle has a width of 1, the delta sub I x is 1, and the delta sub I y is 1. So these are all 1 by 1 rectangles, even though they don't look like it. Anyway, we plug in F evaluated at each midpoint times the delta sub I of A for each one, which is 1 for every single one of them. So I plugged in minus 0.5 for X, squared it, got 0.25, doubled it, got 0.5, plugged into 1.5 for Y, 3 times 1.5 is 4.5, minus a half is the 4 times the 1 is 4. And then I do that for all, that was this one, and I do it for all 6 rectangles, and I get 25, and that's approximately this value of the double integral. So what I'm going to do is just finish this out. I'm going to jump to the chase of how we actually do the double integral exactly, but 25 is the approximate answer. So let me clear this. Hopefully it lets me keep writing. And I want to find the exact value of 3y minus 2x squared dA when we have, what do we say? So the x value is -1 is less than or equal to x, is less than or equal to 2, and 1 is less than or equal to y is less than or equal to 3. Okay, so really what we're going to do is we're going to say, hey, this is my x1, this is my x2, right? And this is, trying to use the same colors, this is my y1, and this is my y2. Okay, and so instead of dA, we can split this up 2 ways. Sorry, I should use black here, but I can split that up 2 ways. I can either take it with respect to y first, then with respect to x, or I can take it with respect to x first and then with respect to y. So long story short, if I've got the double integral over region R of f of xy dA, then I can write that as double integral, and I'm not going to put of xy every time, but dx dy. So the reality is, I kind of want to, since this is the dx would be connected first interiorly, I could consider this a single integral. What I'm going to want to do then is I'm going to want to say, hey, this is from x1 to x2 on this one. And then I would do the whatever I get there in purple or blue for the whole thing. Whatever I get there for that, I'm going to take dy, the antiderivative with respect to y. So then I'll go y1 to y2 for that one. The other way to do it is I could go, if I want to take the double integral with respect to y first, then with respect to x, for my f here, I'm gonna take y1 to y2, take that interior antiderivative first, and then after I get that, then take the antiderivative with respect to x and go from x1 to x2. So let's do that and see how that works with this one here. So I'm going to clear this, come back, draw it out, hopefully. And then I've got the double integral of, once again, we had 3y minus 2x squared. And the book actually does this one later on, I believe, in example, I think they do, example 3. And they do it with respect to x first. I'm going to do it with respect to y first. So I'm going to have with respect to y on the inside and then with respect to x. So if I do the y's first, now remember the y's range from 1 to 3. So y1 equals 1, y2 equals 3, and the x's go from -1 to 2. So the reality is I am calculating this antiderivative first. Remember, if it has a y in it, that's my variable when I'm taking the antiderivative with respect to y. Otherwise, it would be considered a constant. So let's do the red first. And what would we get? We would get the antiderivative of 3y with respect to y is 3y squared over 2. And then minus 2x squared is 2x squared y, because 2x squared is like a constant, right? And so antiderivative of a constant is a constant times y. And this is going to be evaluated from 1 to 3. So let me do that. Now what equals, this is from 1 to 3. Sorry, I don't know where this came from. But anyway, if I plug that in, where am I plugging? The y's range from 1 to 3, so the x's don't change, right? So plug the 3 in first, and what do we get? We get 3 times y squared is 3 times 9 is 27 halves, minus y is 3, so that'd be minus 6x squared, right? So there's nothing to plug in for the x. And then minus, I'm going to plug in the 1 here, and I get, for y, I get 3 halves minus 2x squared. Okay, and remember, subtract means add the opposite, so I'm going to go ahead and do that here, add the opposite, and what do I end up with? I'm going to end up with 27 halves minus 3 halves is 24 halves, which is 12, and then minus 6x squared plus 2x squared is plus 4x squared. That's what I get for the red bracket. So now, what does that mean? Now I'm going to plug that in here and then take the antiderivative with respect to x. So by doing that, I now have the antiderivative from -1 to 2 of 12 plus 4x. Come on, don't fail me now. 12 plus 4x squared with respect to x, and taking that antiderivative, I'm going to get 12x plus 4x cubed over 3, evaluated from what? From -1 to 2. Plugging those in, what do I get? So plug the 2 in. I'm going to do that up here. That's going to equal 12 times 2 is 24, plus 2 cubed is 8, times 4, double it twice, 8 times 4, 32 thirds. And then minus, evaluated when I plug in -1. -1 times 12 is -12, plus -1 cubed is -1, so it's actually minus 4 thirds. Now I'm just going to make my life easier, add the opposite, add opposite, opposite. And so what do we get here? We get, well, somehow this isn't working out correct. Plug in 2, I get positive 24. Yeah, and I plug in -1, I get -12. Anyway, so it looks like 36 plus 36 thirds is 12, and that's not right because that's 48. So, oh my goodness, I messed something up. Did I mess up a minus sign? Yes, I did. It's a minus. You people, minus 6x squared plus 2x squared. And the only reason I knew I messed up is because the answer is supposed to be 24, which is example 3 in the book. But anyway, this was a minus sign here, so we better do that. Correct. Taking the antiderivative, that'd be a minus. All right, that's going to make life a little bit better here, hopefully. So we got 24 and then minus 32 thirds. And then I was going to subtract when I plug in -1. I get minus 12, and then this is going to be plus. So let me just go back. I was subtracting maybe I'm going to use my eraser. That could make life a little easier. Yeah, let's do this. All right, and then go back, draw it in. All right, I was going to subtract, plugging in -1, I get minus 12, and then I've got minus a minus 4/3 is plus 4/3, but I'm going to subtract the whole thing. So subtract means I'm going to use a different color here. Add the opposite. There we go. And now I've got 36. I still have that from 24 plus 12, but then minus 32/3 minus 4/3 is minus 36/3, which is minus 12. So that should have been a minus 12. 36 minus 12 is what we want is 24. And actually anyway, 24 is the exact answer. We had an approximate answer of 25 when we used 6 rectangles before, but this is the exact value of the double integral. So I'm going to stop there. We'll continue on with a different lesson with volume as example 4 and stuff like that. But if it is entirely on or above the table surface, if your function is for wherever we're looking for the x values and the y values, then it's going to end up the double integral of f dA is going to, over that region, is going to give you the exact value of the volume.